this video, we will talk about the application of first-order differential equation as a mathematical model that can be used in biology, chemistry, and physics. But first, we need to discuss what is a mathematical model. What is a mathematical model? A mathematical model is often desirable to describe the behavior of some real-life system, whether it is physical, sociological, or even economic in mathematical terms. The mathematical description of a system of phenomenon is called a mathematical model, and it is constructed with certain goals in mind. For example, we may wish to understand the mechanics of a certain ecosystem by studying the growth of animal populations in that system. Or we may wish to date fossils by analyzing the decay of a radioactive substance, either in the fossil or in the stratum in which it was discovered. The construction of a mathematical model of a system starts with the identification of the variables that are responsible for changing the system. We may choose not to incorporate all these variables into the model at first. We are specifying the level of resolution of the model. Then, we make a set of reasonable assumptions or hypotheses about the system we are trying to describe. This assumption will also include any empirical laws that may be applicable to the system. Once we have formulated a mathematical model that is either a differential equation or a system of differential equations, we are faced with the non-insignificant problem of trying to solve it. If we can solve it, then we deem that the model to be reasonable if its solution is inconsistent or not with either experimental data or known facts about the behavior of the system. We will discuss about the mathematical model for population, specifically the population dynamics. Differential equation can explain the effect of a pollutant discharged into a lake. Also, with the Newton's law of cooling, can aid forensic scientists and detectives in determining the times of death. The focus of this is, however, in modeling in the field of population biology. Basic concepts and mathematical models of population dynamics, including exponential and logistic growth, competition, and predation, will be discussed here in this video. But for most, we will only discuss about the population dynamics, its basic concepts, and some problem exercises. A population is a group of plants, animals, or other organisms, all of the same species that live together and reproduce. How can the size of a population change? There are four factors that can affect the population. Birth in a population increase the size, while death decrease the size. Also, new individuals enter the population, which is called immigrate, or leave the populations, which is called emigrate. A very simple equation represents the statement of it. N is equal to B minus D plus I minus E, wherein N is the change in population size, B is the number of births, D is the number of deaths, I is the number of immigrants, and E is the number of emigrants. The simplest model is when the growth of a population is considered to be density independent. Density independence means that the birth and death rate are not affected by the population size. Therefore, the rate of birth and deaths is proportional to the number of individuals in the population. A constant R will now be introduced, which is the instantaneous rate of increase or intrinsic rate of increase, such as dn is equal to rn, or dn over dt is equal to rn. In words, the above equation says that the growth rate dn over dt is proportional to r. The factor r is important because it determines if the population increases exponentially, is constant, or decreases to extinction. In order to project the size of a population, the following derivation is required. N of t is equal to the population size at time t. N with the base O is the initial population size. E is the base of a natural logarithm. T is equals to time. And R is equals to the intrinsic rate of increase. As example, we study some basic models in population dynamics of a single species. Without interaction with other species, the change of the population y is equal to y of t can be assured to only depend on the population itself. dy over dt is equal to f of y.
Now we're going to talk about exponential growth and decay problems as it relates to population growth. Now the first equation we need to be familiar with is this equation dp divided by dt is equal to k times p. So this equation tells us that the population grows at a rate that is proportional to the size of the population. The population growth rate is dp dt, that's how fast the population is grown at a given time k is the relative growth rate, and the p is the size of the population at some time t. Now for us to understand this, how can we derive a general formula to calculate the population at any time? In order to do this, let's multiply both sides by dt so that these two will cancel, and so we have dp is equal to kp times dp. Now, we need to separate the variables k are constant. As you said, it's the relative growth rate. We need to separate p from dt. So let's divide both sides by p. So now we have this expression 1 over p dp is equal to k dt. At this point, let's integrate both sides. The antiderivative of 1 over p is simply the natural log of p. K is constant. The antiderivative of dt is t, so this is going to be k times t plus the general constant c. So what should we do at this point? Now that we have this equation, how can we get t by itself at this point? At this point, you want to put the equation on top of e, that is on the x alone, even if ln it is even if ln t is equal to kt plus c, and then e raised to the ln p is equal to e raised to kt plus c. Now the base of a natural log is base e, so these two will cancel, and the p is equal to e raised to the kt plus c. Kt is added to c, so therefore what we could do is we could say that e to the kt plus c is equal to e raised to the kt times e to the c. Now even if ln t is equal to kt plus c, and then e raised to the ln p is equal to e raised to the kt plus c. Now the base of the natural log is base e, so these two will cancel, and so p is equal to e raised to the kt plus c. Kt is added to c, so therefore what we could do is we could say that e to the kt plus c is equal to e raised to the kt times e to the c. Now, e to the c is a constant, so we could simply replace it with c. So the population is equal to c e to the kt. Now starting with this equation, we're going to calculate p of 0. So let's replace t with 0. This is going to be c e to the k times 0. K times 0 is simply 0, so this is going to be c e to the 0. Now anything raised to the 0 power is equal to 1. So therefore p of 0 is c times 1, so c is the initial value. It's the population at t equals 0, so we could say c is basically p initial. Thus we can replace c of t initial. So the general equation is the population at any time is equal to the initial population t sub 0. E times the relative growth rate, which is k, multiplied by t. So now you know how to derive this formula from this equation. Let's work on this problem. The table below shows the growth of population on a certain island where t is the number of years beginning with the year 2000. Determine the relative growth rate. So we need to use the equation p of t is equal to p of 0 e raised to the kt. Our goal is to solve for k, but first we got to find p sub 0. So what exactly is p sub 0? Well, p of 0 is equal to 1000. When t is 0, that is the year 2000. The population is 1000. So if we replace p of t with 1000 and t was 0, we're going to get 1000 is equal to p sub 0. E to the 0 is 1, so p sub 0 is 1000. So p of 0 is the same as p sub 0. That's the initial population. So how can we use this to calculate k? So now that we have a value of p of 0, we can say that p of t is 1000. That's p sub 0 e kt. So now let's use another point to calculate k. We can use any point in the data table, but let's use the first one in the year 2001. T is equal to 1, so the population at t equal 1 is 1250. So let's replace t of t with 1250, and let's replace t with 1 in order to solve for k. Let's divide both sides by 1000, which is equal to 1.25, and that's equal to e raised to k power. Now we need to take the natural logarithm of both sides. The natural log of e to the k, what do you think that's equal to? A property of logs allows us to move the constant or the exporting the front. So this is equal to k times the natural log of e, and the natural log of e is equal to 1. So k is simply equal to ln 1.25, which is about 0.223. So that's the value of k. Now we can write a general formula. So to write the general formula is going to be 1000e, and then all I need to do is replace k with 0.0223 t. So that's the answer to part B. That's the general equation that will give you the population p of t at any time. The answer to part A, the relative growth rate, is the value of k, which is 0.223. So basically the population increases by 22% every year, compounding continuously. This formula is the general form of the compound interest type problems. Now, how can we estimate the population in 2008? To do that, simply replace t with 8. So this is going to be 1000 e raised to the 0.223 times 8, and just type it in your calculator exactly the way you see. And the answer is 5953. In the year 2008, now, how many years will it take the population to double? And that's starting from the year 2000. What we're going to do is we're going to find out how long it takes for the population to double from 1000 to 2000, because 1000 times 2 is 2000. So let's replace p of t with 2000. We just gotta solve for the variable t, so let's get rid of a few things. So our first step is to divide both sides by 1000. 2000 divided by 1000 is simply 2. So 2 is equal to e raised to the 0.223 times t. Next, we need to take the natural log of both sides. This will allow us to take this exponent move to the front. So the natural log of 2 is equal to 0.223 times t multiplied by the natural log of e. And the natural log of e is 1. So ln 2 is equal to 0.223 times t. So the time it takes for it to double is simply ln 2 divided by the rate constant k, the relative growth rate. So if we divide these two numbers, ln 2 is like 0.6931 divided by 0.223. So it's going to take 0.310 years in order for the population to double. Let's round that to the nearest whole number. So approximately 4 years, or we could say by the year 2004, the population will be above 2000.